Hello? Good morning. Can people hear me? All good? Okay. Yeah, so if anyone can't hear me, please let me know. Um, okay, so welcome to the second week. And as a reminder, the programming assignment will go out today, right after the class. And please sign up for your groups by the end of the day. So to do that, you go on Canvas, and then there's like a People tab in the side, and you just put your name in the group that you want to join. If you want to work alone, that's totally fine. But if you want to work alone, please sign up for a group also, because I will randomly assign everybody that's not signed up. So to avoid that, if you want to work alone, feel free, but just sign up. And yeah, that's pretty much it. So the contract is due at I think on Friday, and you can, it's open on Gradescope. You can submit it anytime, but if you submit it on Gradescope, please also add your group members into the assignment. So like there's a place for you to do that somewhere there. Yeah, any questions, any issues? People are able to see the homework? Yeah, so we did the first part of the homework, like the first couple of questions last time, or like the material to do them last time. Sorry, we didn't do the questions, but we will do the material to do the second half today. And everybody okay? Any concerns? Yes. Oh, okay. Is that better? Okay, great. Thank you. Can people hear me? Better? Okay, great. So today, last time we did analysis of general parallel algorithms, like these notions of speed up, efficiency. And today we are going to do analysis of multi-threaded algorithms. So they're related measures, but they're not exactly the same. So let's get started. So today we'll be studying a model for multi-threaded algorithms called binary forking. And binary forking is a model where you have threads, you have parallel threads, and they can be created dynamically. And so basically the way it works is that at the beginning of time, in the start of your program, you have one thread, just like a normal algorithm, and you start executing the lines one by one. And at some point, you can introduce these parallel constructs, which I will introduce shortly. And the parallel construct means that you can do two parts or more, depending on how you do it, simultaneously. And that's something that you write in your algorithm, like you identify parts that can be done independently. And this is just an analysis model for when you write your algorithm in such a way. And every thread acts like a standard RAM model. So this is the way that you learn algorithms in any introductory algorithm class, is in something called the random access machine model, which is that you have some number of registers and you can access the memory in constant time. And reminder that we are working in the shared memory setting today. So shared memory machines, you have a bunch of processors and they're connected by the shared memory. And one thing to notice is this is a theoretical model, so you can spawn as many threads, like logically, you can make as many threads as you want. And the number of threads does not have to be related to the number of actual processors that you have. When you actually have programming systems, like from the programming level, you say, I want this number of threads, and somehow some underlying scheduler will arrange the threads into the actual physical processors that you have. But you don't, like this is a theoretical notion, and so you don't have to worry about this assignment. So the main constructs in binary forking are just a few simple operations. The main operation is called a fork, or also called a spawn. So that's why it's called binary forking. And the reason that it's called binary forking is because in this model, you can spawn one parallel thread at each time. And so this spawned thread is asynchronous to the original thread. This is called parent thread, and this is the child thread. And both of these, remember, are independent, like RAM machines. Like, for example, you could run two independent copies of an algorithm, and they can run in parallel, and they don't have to access the same memory. They can, if you want, depending on the algorithm, but they don't have to. And then, so there's a spawn, and this is how you identify parallel work that can be done. And then if they need to sync, which is like all threads need to reach some point before the algorithm continues, which is something that you might want to do, like you need some sub-answer before you move on to computing the rest of the answer, then you sync, which means that all threads have to reach this point before they all continue. And at this point, after a sync, there's only one thread left. All of them have reached this state, and they all synchronized into one thread, and then you can continue spawning later on if you need. The computation starts with one thread, and it finishes when all the threads end, like you reach the end of your program, and all of them have finished their work. And the reason that we're studying binary forking is that you actually have these programming constructs in languages like Silk. Java supports some kind of fork join model, Habanero, which is another thing, and then Intel TBB, which is thread building blocks. So these are all popular programming models for shared memory. Question? Can you handle it not finishing? Like the threads will proceed asynchronously, and some of them may be faster than others. But sync means that they all have to reach this point before the program continues. So some may reach it faster, some may reach it slower. But sync just means nobody can continue until everybody reaches that point. Mm-hmm. Could you say more? Sorry. So you mean like if, so like let's say you start with one thread, you spawn one thread, and both of them are doing something. Could you repeat the question? Like, is the question that can both of them access the same resources, or can you access the resources that spawned it? Mhm, mhm. Oh, I see. Yes, that's probably more in the implementation level. Yeah, depending on the implementation, different programming languages can deal with different, like deal with the actual logic of the thread being alive or not. For now, let's just focus on the theory part. And for the theory part, this thread, like even if it finishes the work, let's just assume that like it doesn't crush the program, and that yeah, these are just like high level constructs that can be implemented, that need to be implemented by some lower level programming system. Thank you. Does that make sense? Any other questions? Okay. So like as you can see, this is a pretty, there's only two constructs. There's only spawn and sync, but it turns out that this is a pretty powerful abstraction, and you can implement a lot of parallel algorithms in this way. Okay, so let's do a small example. Let's consider this fib example. So we want to compute the Fibonacci numbers. And this is a divide and conquer algorithm to compute the Fibonacci numbers. Of course, we have better algorithms to compute fib, but it's for illustration because binary forking fits really well into divide and conquer algorithms. And so this is just for illustration of how you would write spawn and sync in an actual program. So fib, one way to illustrate it is through recursion. You start with n, which is like you want to compute the Fibonacci numbers up to the nth one. If n, your base case, is less than 2, you return n, like the fib numbers 0 and 1 are just 0 and 1. And otherwise, we have x and y, which are computing, oh yeah, this should be like x equals this and y equals this. But let's pretend that I did that. So x equals fib of n minus 1, y equals fib of n minus 2, and then in the end, to get the fib number, you add up the recursive answer, fib n minus 1 and fib n minus 2. And this is how you write the spawn and sync. So you spawn off this fib of n minus 1, which can be computed independently of fib of n minus 2. And then in the end, we need to do a sync because we need both these sub answers to compute the sum at the end. Mm-hmm. You need to spawn the first one. It can be, like this could be fib of n minus 2 and this could be fib of n minus 1. But if you write the spawn in the second one, then this part will proceed in serial and needs to complete before we spawn off the second one. And then the parent thread has nothing to do. So this spawn is getting forked off into the child. And then the continuation, which is like the parent is still going, is now going to start here and do this n minus 2 part. So it doesn't matter which fib call was in the spawn, but the spawn needs to be the first one. Yeah, good question. Otherwise, you accidentally serialize the whole thing. Other questions? Does this make sense? Yes. Yeah, let's just say this is X and this is Y. They could be flipped, I guess, but does this make sense? So this is going to these two calls, fib of n minus 1 and fib of n minus 2, are going to proceed in parallel to each other because they don't have any dependency. And notice that this is recursive. So when fib of n minus 1 comes into here, it's also going to potentially spawn. Now, like n minus 1 is going to be the input here. So the two subcalls there are now like n minus 2 and n minus 3. And n minus 3 will get forked into the spawn, and then n minus 2 will get forked into the spawn, and n minus 3 will get in the continuation. Yes, n is a shared variable, but no, there's no writing to n. N is just reading, so it's not a problem. N is just the input. Everybody can access that, and then like the parameter that gets passed in would be different in the different recursive calls. So like let's say here we're starting with n equals to 4. The next time when we come back in this recursion, we're going to start here with n equal to 3. That's just like a local function variable. Yep. Okay. So the way that we visualize in the binary forking model is called this computation DAG. DAG is a directed acyclic graph. And the edges in the nodes are like the function calls. And the edges are spawn or sync or continuation. And these are just like, I illustrated this. This is like this is the block where n equals to 4. This is a block where n equals to 3, n equals to 2, n equals to 1. Like that. So starting from fib of 4, this is the first function call. We pass in fib of 4, and then fib of 4 is going to have two subcalls, fib of 3 and fib of 2. So this is fib of 3, and this is fib of 2. And then this is 3, which is getting here in the continuation. This is 2, which gets forked into, 3 gets into a child thread, and then 2 is in the continuation here. And then, like I said, recursively, 3 has the same story. So it spawns 2, and then it does 1 in the continuation. And then the same, again, recursively with 2, you go into 1, and it just returns. And this blue one also has subcalls. Like here, this blue one, this is fib of 2, and so it goes into this part. And so the computation DAG, you can think of the circles as operations or function calls. And in some sense, then to do the analysis, we think of this DAG as the entire algorithm execution, and we want to analyze measures on it. The dark blue circles are sync. Yeah. So this is like this would be like spawn. This is spawn of n minus 1. This is spawn, or this is continuation of n minus 2, and these two are syncing back into here. So this is like the dependencies, and so like this spawn of n minus 2, or sorry, the spawn of n minus 1 needs to finish before we do the continuation of n minus 2, because this is how the code is written. Spawn of fib of n minus 1, we have to finish this line before we go into this line. Like the actual function call to n minus 1 does not need to finish. Like you can see that this is parallel to this, but the spawn of it needs to finish. Like it needs to begin on the child thread before you can start the work of this part. So yes, there are better. Yeah. So this is one important thing to note, that often, like last time we talked about work efficient algorithms. This is clearly not work efficient because the best serial algorithm, as you noticed, is linear. This is not linear in n. So this is one thing that is an issue sometimes with parallel algorithms, is that you pay in work efficiency. There are parallel work efficient algorithms for fib, but they are more complicated. This is just to illustrate. The binary forking paradigm, especially to illustrate the computation DAG, because this is like a simple recursive algorithm. Good question. So this is parallel spawn of fib n minus 1. And then like parallel spawn of fib n minus 1 is just this function call again, but it's just on a different thread. So this is the different thread that is going to execute fib of n minus 1. So the computation DAG is not, the computation DAG and the assignment of these nodes into processors are independent. Like the computation DAG is just a logical representation of the work and the dependencies that need to happen. The programming system is responsible for assigning this into the actual processors. But from a theoretical perspective, we're just using this to analyze, like we can use this to analyze the work and how much possible parallelism we could get. It's unrelated to the actual number of processors you can have. Yes, yeah, this is shared memory. So yeah, like here we have x and so typo, but we assigned x into fib of n minus 1, and we assign y to fib of n minus 2, and then in the end we add them up. Yeah. Yes. This one? Mm-hmm. Mm-hmm. But this is the edge to the two. Like for fib of n minus 1, or sorry, this is fib of n minus 1, it calls fib of n minus 1 here. And that again calls fib of n minus 1, which is this fib of n minus 1 here. Because this is fib of n minus 2. Yeah, so this is just like a function call. This is again fib of n minus 2 here. Yeah, the nodes represent like a, you can think of it as like a line. Like the edges can be either spawn, sync, function call, or dependency. Or like, yeah, like for example, these two have dependency. Mm-hmm. Yes. Sorry, this one and this one? Mm-hmm. Yeah, because this fib n minus 1 is in the same thread. This is in like the original parent thread because it didn't get spawned. However, like when you come back, you notice that when you come back around here, like this calls back in here, and that may spawn something else. So like the original call to fib n minus 1 or fib n minus 2 was in the continuation, which is like just the original parent. But when you come back around, it may get spawned into here. And parallel spawn and sync are not, depends on the implementation of the programming system, but like they just indicate that they can be run in parallel. The actual assignment into the parallel processors is independent. So like they may not necessarily be run in parallel, but they just can be run in parallel. And so from a theoretical point of view, we're just saying like what is the maximum amount of parallelism we could achieve, not what is the actual assignment of this into processors, which is complicated. Mm-hmm. Yes. Because it's the operation on the same level, the assignment can be just because they're on the same level. No, like you think of it as like, you can kind of think of it as like a DAG. So this is like the start of the DAG. And so anything in the same level or anything in parallel in the DAG that doesn't have dependency can be run in parallel. This is just a way to indicate parallel flow. Okay, so this is a more concrete version of this. A parallel, so this is just a DAG representation of, like I said, the parallel workflow. And the vertices are called, more formally, they're called strands, which is a sequence of instructions. It can be one instruction, it can be a bunch of them, which doesn't contain spawn, sync, or return from spawn. So this is the initial strand. And then an edge is either the spawn, a function call, the return, or continue. So here it's continue because this was like n-1, this is n-2. This was spawn because we spawned n-1 into this function. This was sync because we have to sync into this thing. And yeah, so notice that we are only using spawn and sync constructs, but later on we'll talk about how you can implement parallel for using just spawn and sync. Strand is like a logical, like this computation DAG. A strand is like a logical thing that can be assigned to a thread. And in the actual programming system, of course, we will have to assign the parallel work into different threads. But that's, we're not going to think about the assignment because that is up to how the programming language is implemented. This is like a high-level theoretical notion of like what can be run in parallel and what needs to be run sequentially. Okay. So yeah, so we're going to introduce these notions of, we want the high-level goal, like the reason that we're talking about this is that we want to theoretically analyze how much parallelism or maximum speed up we could possibly achieve in a parallel computation. Because like the goal of parallel computing is to achieve speed up on more processors. And so using this computation DAG abstraction, we want to analyze what is the parallelism of the computation, or how much possible speed up could we achieve. And we're going to assume that each strand can execute in unit time. Okay, so to know that, we can use, again, we talked about Amdahl's law in the beginning, which is kind of like one of these basic laws in parallel computing. It has these two parts, or a few parts, 3, I guess. But this one is a function of the first one. The total work is 1. S is a fraction, less than 1, or at most 1, which is something that has to be done sequentially. And then 1 minus S is the work that can be done in parallel. And then let's say you have a number of processors P. And the speed up is the time on one processor divided by the time on P processors. And then using this small derivation, we can get that the speed up is bounded above by 1 over S. S is the serial fraction. So this is saying that if, kind of intuitively, if you have more sequential part in your program, you can get less parallel speed up. It's like you can't make use of the parallel resources. And for a fixed problem, the upper limit of the speed up is determined by the serial fraction. However, like Amdahl's law is, it sounds nice, but like it's a bit hard to use practically because like it's somehow hard to measure the serial fraction sometimes, in the sense that like, let's say you had an actual program, like how would you measure the sequential part? Like you could measure the time, you could count the number of lines, but like the serial part, like the time is not exactly a good measure because like this parallel part may be faster than the serial part because it ran in parallel, even though like in the total volume it had more time or less time depending on the relationship. So there's some subtlety about how to actually measure this the serial fraction. So that's why we're introducing these other theoretical notions of computation DAG. Okay. So to quantify parallelism using binary forking, we introduce this notion of the computation DAG. And let's say that we have this example computation DAG. We have this start. This is our starting point. We had one sequential step next. And then let's say that we had some fork. Like this is a spawn. And these two parts can now run in parallel. And each of these can also fork off different work. So this now again does a fork. And this one also again. So it can be done, forking can be done recursively, is the point. And using Amdahl's law, like this is nice because we have a nice theoretical DAG here. And using Amdahl's law, the serial fraction is 3, because these are the sequential part. This entire part can be run in parallel. And the total number of nodes is 18. So using Amdahl's law, the serial fraction is 3 by 18, which is 1 over 6. So the speed up would be bounded above by 6. But like I was saying, like this is a theoretical thing, and if you actually had this program, it would be a bit hard because like you would measure this part, and then you would measure the time for this, and the relationship between them may not be 3/18 because this part ran in parallel. So that's why it's a bit hard. It's not like impossible, but that's why it's a bit subtle to use when you actually have programs. Yeah.
So theoretically, we're saying that the part that is in gray takes no time?
Theoretically, we're saying the part that is in the gray can execute in parallel. Like this path through the DAG can execute, like these two nodes can execute in parallel to each other. But this node depends on this node. So this node must complete first. Sorry, this node must complete first before this one or this one starts. The lines in the, like the edges in the computation DAG are dependencies. Yeah, so that's what you would get from Amdahl's law. We're going to introduce two new measures using the computation DAG. So the first is just the serial work, which is just like the work that you would get on a single processor, or the total time. The work is the time on one processor. The goal that always the goal in parallel computing is that we want to minimize the execution time on preprocessors. So yeah, the work here is 18 because there's 18 nodes, and we're going to assume that each one executes in unit time. And the new measure, this is like this is the new part in parallel computing, which is that we want to measure something called the span, and it's sometimes also called computation depth. And the span is the longest path through this computation DAG. And in some sense, the span is the amount of time that it would take you if you had infinitely many processors. So notice that P, the number of processors, does not show up in the span. It may show up in the actual practical speedup, but it does not show up in the span, which is like a theoretical, it's a theoretical notion of the maximum serial path through this computation. Yeah. We're just assuming that each node is unit. So here, there's 18 nodes, so the work is 18, and the span, you can just count the path lengths, and you would take the maximum path length through this DAG, and here it is 9. And span is sometimes called critical path length, or it's called depth sometimes. This is just an example DAG. So it could, like, to measure the span here, you would count all of the paths through this DAG, and you would take the maximum length over all those paths. And I just highlighted the maximum length one.
So if I choose
span is the maximum computational path length. Yeah. So each of them, like, we will have to go through each of these paths because all of those paths, like this DAG is the work that needs to be completed in the algorithm, but the span is the longest one. And the reason that we are interested in it is because it is related to how much possible speedup we can get, because we always have to go through the span. In the end goal, we'll get to some examples, but in the end, we want to express both work and span in terms of n, which is an input to the algorithm. Just like when you do regular algorithm, or when you do like serial algorithms, you express your answer as a function. You express the time as a function of n. Like sorting is n log n, for example, or like matrix multiplication is n cubed. In a similar way, we express span as a function of n. Yes. Yeah, good question. So here, the serial fraction was 3, because the serial fraction doesn't count any part that can be run in parallel. But this, yeah. So that's not counted in the serial fraction. But span does count. Span is like, you can think of it as the longest chain of dependencies through your computation. And so the thing that, so I find it easy to think about span as like, if you had infinitely many processors, how long would your computation take? Like this part has dependencies and they cannot be parallelized because this is how the computation DAG is. And so even if I had, I don't know, 1,000,000 processors, I can't speed this up. Does the serial fraction change as n changes? Depends on your program, probably. Like if the parallel part grows. Mhm. Depends on how this DAG changes with n. Like this DAG is the computation DAG for a fixed n. And it may look different depending on what n is. Because like it depends on your algorithm, what is in the parallel part and what is in the serial part. I think we can't say because this is like not based on an actual algorithm. This is just like an example DAG. So in an actual algorithm, like the serial fraction might change. It might not also. Uh-huh. How do you determine the serial fraction based on the DAG? You can, yeah. Like in your program, you have some lines that are serial and some lines that can be run in parallel, depending on where you put the spawns. And so the lines that are serial, like the lines that are sequential, are the serial fraction. Mhm.
I would say look at layers which have so it's like the first one has only one layer, the third one has only no parallelism happens at the
Thanks. So are these measures clear to folks? The work in the span? So going forward, like we're going to use these measures, but they're going to be expressed in terms of n, because n is like the input size to the algorithms. Yeah, and there's a couple of laws. T sub p is the time on p processors. The work law says the time on p processors is at least the time on one processor divided by p. This is saying, another way to say this is we get at most linear speed up in p, which we said last time. And then the span law is the time on p processors is at least the span. So like I said, the span is the time on infinitely many processors, and p is less than infinity. So you cannot, the span is like the minimum, in some sense, like the minimum amount of time that this is going to take. Okay. The way that we compose work and span, work is just in serial algorithms. Like we have two parts of your program, A and B. The work of these two components put together, the work of A plus the work of B. Here, because they are in series, the span of A and the span of B are also added up. This is like dependencies. So first we have to finish A and then we have to finish B. And the span is just the span of A plus the span of B. Okay, but if you run them in parallel, let's say we have A and B that need to run in parallel. The work is still if you sum them both up. So work of A plus work of B, because the work is the time on one processor. So if you have one processor, you would still have to do this, both of them. You can't make that faster. But the span, if you have two things that are in parallel, is the max of both spans. So this is max of the span in here and the span in there. That makes sense? Because like imagine that each of these had a computation DAG inside. And so the span is the maximum path through the computation DAG, which is the maximum path in here, the max over the max path in here and in here. Yeah, we talked about this last time. Speed up is T1 over TP, where T1 is the time on one processor, TP is the time on p processors. Ideally, we would like to have p speed up. That's like the best case scenario. In practice, we can have super linear speed up, but in theory, due to the work law, we cannot. That's like a practical thing. We would like to achieve p. Okay. And then we also talked about Brent's law last time, which said that you can simulate any, if you have n processors, you can achieve that efficiency on any number of processors less than n. It doesn't, like, you have to be careful about the order. Like, you cannot simulate more processors. Like, let's say you had p processors, you cannot simulate the algorithm on 2p processors and theoretically guarantee that you can get the same speed up or efficiency. Because, like, on p processors, last time we were saying, like, oh, let's say it takes this amount of time on p processors. That is based on which parts can run in parallel and which parts cannot. And you cannot necessarily further parallelize onto 2p processors to get equal efficiency. So you have to be careful about the direction in which you compare the number of processors. But anyway, so yeah, so the reason that we are analyzing work and span is because the span is, yeah, so the binary forking model and also the span are related to the time on infinitely many processors. And clearly, we will have a number of processors less than infinity. So due to Brent's law, then we can simulate, if we have the span, which is related to the speed up on infinitely many processors, then we can simulate it on fewer processors. Yeah, and this is another formulation of Brent's law, which is time on p processors is at least serial time over p and bounded above by serial time over p plus the span. Okay, and parallelism, this is the end goal that we wanted. The parallelism, which is like the amount of speed up that we can, the maximum amount of speed up that we can get in the limit is just the work divided by the span. And more formally, the reason that we're doing this division is that it's kind of like the amount of work for every step of the span in some sense. So like you want to maximize the parallelism because then if you have more processors, they can all do different stuff at each level of the computation DAG. Mm-hmm. Okay. So this is like the minimum time that this can take. And yeah, so it's bounded above because it's going to take at most, because the computation DAG, this is the longest path through the computation DAG. And then this is the speed up that you can get on the rest of the computation DAG, not counting the span part. Make sense? Thank you. Okay. Yeah, so going back to this fib example, the work is 17, the span is 8, and then the parallelism is the work divided by the span, which is about 2. And this is telling us that here using more than 2 processors for the case of n equals to 4 is not going to give us really anything because there's at most like 2 units of work per step of the span, and so adding more processors is not going to help. Questions so far? Okay. So we're going to move on to a different problem. Hopefully everybody is familiar with quicksort. Quicksort is a randomized sorting algorithm. The expected serial time is n log n. And this is some pseudocode, ignoring the code for partition, which is like, in quicksort, every level of the recursion, you set a random partition, and then you shuffle like stuff less than that and stuff more than that into the left and right halves. And you hope that you picked somewhere in the middle. In quicksort, the base case, so you have pointers to left and right. You exit if left equals to right. Otherwise, you have this recursive call. You partition based on the left and right endpoints, and then you spawn you recurse serially. You recurse into both halves, first the left and the right, but it doesn't really matter what order you do them in. But in parallel, we can spawn the left and the right halves, because like the recursive call can happen independently. Like after we have partitioned left and right and we have done the correct shuffling, the two halves are now independent and they can be worked on in parallel. So that's why there's parallel spawn. And so this is the left half, this is the right half, and then we call sync. What is the expected work and span in binary forking? And let's assume that we don't have a parallel partition algorithm, and so partition is going to take theta n work and span. Maybe we can start at the easy part. So what is the work? The work is the time on one processor. And the way that you calculate the work, you just kind of like ignore any part that says parallel spawn or parallel sync, and you analyze how long it's going to take you. Mm-hmm. Yes, good. And how about the span? Is the span log n? Why is the span log n? Mm-hmm. Mm-hmm. Yeah. Yes, exactly. So the number of levels of recursion is log n, but the span is like if you add up the span at every level of the recursion. And so let's just consider the first level of recursion. Even before we do any recursive call, the partition span is n. So the total span will be at least n, because the span of the first call is n already. And now we want to think about the span in the lower levels. So now let's say that we picked a nice partition, and now the left half is half. And then we come back around, and what is the span of now this new partition call on n over 2? Like just in the second level. The input size, let's say, is theta n over 2. Mm-hmm. Yeah, exactly. So the span of this call to partition in the second level is n over 2, assuming that left and right are separated by n over 2. Because we are assuming that partition has linear work and span in the size of the endpoints that we gave it. And then by a similar logic, the next level would be n over 4, because we cut the problem size in half again, and all the way down, like n over 8, n over 16, that are all the way down to theta 1. And if you add them all up, n over 2, n over 4 is, you can give it a theta notation. Mm-hmm. Mm-hmm. Good. Yes, so the expected work is n log n, and the expected span is theta n. And then parallelism, you divide them. Work divided by the span is log n. Oh, yeah. Questions on this part? Okay. Yeah, so we're not going to go through this, but this is like just a table of work and span of some common algorithms. You don't have to remember this. It's just like a reference sheet. All right. So the next part, so binary forking fits well into divide and conquer. And so one thing that we're going to do now is give formulas for how to solve divide and conquer recurrences. Right. So do people, like, has anybody seen this master method, master theorem? A couple people? Some people. All right, great. But not most, so we can, this is good to know. So the master theorem, or master method, is a way to solve, it's a closed form way to solve divide and conquer recurrences of this form, which is t of n equals some constant a times t of n over b plus f of n. F of n is some function b, a and b are both constants. Both a is at least 1, b is greater than 1, and f is asymptotically positive. And the base case is T of n equals theta 1 for some sufficiently small n. Okay, and the way that people prove the master theorem is through analyzing the recursion tree. So we have this recurrence of the form a times t of n over b plus f of n, and we start at the very top with t of n. And there are b subproblems, or sorry, there are a subproblems, and each has size n over b. So this is like one level of the recursion tree. You kind of like, you have a subproblems, and then each has size n over b in the input size. And we had this plus f of n, which is the work at every level of the recursion. So this is if you unwind the recursion one level, we had to compute in time f of n, and now we have to consider all of these, the time in the subproblems. And if we unwind at one more level, there's again a subproblems. Each of these now has size t of n over b squared. And then you keep going until the base case, t of 1. The height of this thing is log base b of n, because we started with n, we cut in b parts every time, and so the number of cuts that we have to do to get to 1 is log base b of n. The number of problems at every level multiplies by a every time, because we have a fan out. So like at the first level, we just had 1, which takes time f of n. The second level, we have a of them. Each of them now takes time f of n over b, because that's just the input size at the second level. And same here, now we have a squared subproblems, but each of them takes time f over n over b squared. And at the leaf level, we are going to have a to the power log base b of n. A is the fan out, log base b of n is the height. So that's how you get the number of leaves in a tree. And then times t of 1, and we said that t of 1 is theta 1. So this is just theta, this is just log exchange. So n exchanges with a. N to the power log base b of a. And the idea behind the master theorem is that we compare this, which is the number of leaves, with f of n, which is the work that you have to do at every level. Okay. There are 3 cases in the master theorem. The first is that the work is geometrically increasing down into the leaves. And so that means that the work is dominated by what is in the leaves, and whatever is above is small order terms. So this is the case where n to the power log base b of a is much greater than f of n, which means that the work up here is much smaller than the work down there. And so the total solution to the recurrence is theta n to the log base b of a, which is the number of leaves that we have. The second case is that the work is arithmetically increasing. Oh yeah, okay. So one example for something in case 1 would be like divide and conquer matrix multiplication. You have 8 subproblems at every level. 8 subproblems. Each of them gets divided in half. And so there are n cubed leaves, which is much less than whatever is happening above. Case 2, something that is arithmetically increasing. So that means that if the number of leaves that you have is similar to f of n, then specifically your function f of n, which is the work at every level, is big O of the number of leaves times log to the k of n, where k is some constant. Then the solution is the number of leaves times log to the k plus 1 of n, because there are log levels. Each of them takes this amount of work, and so you multiply them, you add them all up. Mm-hmm. Sorry, y is n to the log b of a. Oh, yeah, this is just log rules. Like log rows, you can exchange what's in the log without what's outside the log, like with what's in the base. Oh, like this a to the log b of n is this n to the log b of a, and then you multiply each one of these times takes time theta 1. Yeah, and so that's where this theta comes from. Because the base case is t of 1 equals to theta 1. Good. Yeah. So something there's in this case of the master theorem, you can prove like merge sort in case 2 of the master theorem. And then finally, the last one is geometrically decreasing, which is that the number of leaves is much smaller than, yes. Oh, yeah, so f of n is this thing, like log number of leaves times log to some power. And you have to do this at every level of the tree, and so there are log levels. So that's why it's +1. And finally, the last case of the master theorem is the work is geometrically decreasing, going down to the leaves, which means that f of n, which is the amount of work at the top of your tree, is much more than the number of leaves, and so the work is dominated by what is at the top, theta f of n. And then there's some condition on the constants, but yeah, the more important part is this, which is that f of n, which is the amount of work that just happens at the very top level, is omega of n to the log, this is the number of leaves, n to the log base b of a, plus epsilon, for some constant epsilon, which means that this is polynomially bigger than whatever's in the leaves. So this is just a recap. There's 3 cases. This is geometrically increasing. All the work is at the leaves. This is arithmetically increasing. There's like equal-ish amount of work at every level, and so you just add them up. They're log levels. And then this is decreasing, so all the work is at the top. Mm-hmm.
Why is the power the log given
Because f of n is in the arithmetically increasing case, f of n is in some sense the amount of work that you have to do at every level of the recursion. And so there are log levels of recursion, so the total volume of work is log times what you did at every level. It's like summing up all the work at every level.
Why
Because this is this thing times log n. Like it just goes to another +1 in the power. Mm-hmm. Okay. Yeah, so here are a couple examples. Let's say we have this recurrence, t of n is 4 times t of n over 2 plus n. So here f of n is n, a is 4, and b is 2. So n to the log base b of a, log base 2 of 4 is 2. N squared is much bigger than n, so we're in case 1. The work is dominated by the leaves, so the solution is theta n squared. However, if f of n is n squared, so we're just comparing the number of leaves with this amount of work at every level. Here, n squared is equal to, k can be 1, or sorry, k can be 0. So n squared is equal to n squared log to the 0 n. This is case 2. So the total solution is log to the k plus 1. K was 0, so k plus 1 is 1, and that's n squared log n. And we got that because we compared n squared with n squared, which is n to the log base b of a. And then case 3, 4. So this is always the same. A and b are always fixed. A is 4, b is 2, and f of n is n cubed. And so we're comparing n squared with n cubed, but all the work is at the top because n cubed is bigger asymptotically than n squared. So t of n, the solution is just theta n cubed. And the last one, this function f of n to the n squared log n is hard to compare with n squared. It doesn't fit into the three cases, so the master theorem does not apply, but you can prove it by substitution. You won't have to do this. It's just a little extra. Because log to the, so if we go back to case 2, we were comparing f of n is n to the log base b of a log to the kn. And here f of n was n squared, and log to the log base b of a was also n squared. Because log squared, because like this was 1, because k was 0. So then we just put k plus 1 in there. You have f of n, and you have you have n to the log base b of a. And so you just compare them, and if they're off by log factors, then you know what k is. Questions on that part? Okay. So now we're going to do parallel loops, which is just, we can implement them using spawn and sync, just like in a binary tree. Because parallel for is like a common thing that we want to use in parallel algorithms. Like one thing that is really common that you want to express is that you have a bunch of loop iterations and they can all happen independently. And a parallel for loop in the binary forking model has span log n. This is just to say the actual for loop itself has span log n. This is not counting what is in the for loop. But the actual act of making this parallel for has span log n in binary forking. And this is just a side note, binary forking is not the only model for shared memory algorithm or for shared memory multithreading. But there are other models, but they are at most log factors off of each other. And the reason is because in other models like PRAM, the span of a parallel for is 1, and here the span of a parallel for is log n. So that's where the log factors come from. But in the exam, I'll just ask you like which model to use, and it will be this one because we're doing it. Okay, so yeah, this is a parallel for. So here would be the span of the parallel for itself would be log n, and then the span, like the total span would also depend on what the span of foo is. Okay. So we're going to do an example. Let's say we want to do matrix transpose, which is you have a matrix indexed by I and j, and we are going to swap I and j. So like the result matrix has j and I swapped in the indices. And one way to do that, this is just the serial code. You have two for loops. One is over I, one is over j, and you just swap. You put aij in temp, and you swap aij with aji. Notice that the second for loop only needs to go up to I, because you only need to consider the lower triangle, because like you're already swapping with the other upper triangle. But the total volume is still n squared. Okay. Let's put a parallel for here on the outside. And then remember that the span of the parallel for itself has span log n. And yeah, so what is the work in the span in this binary forking model? So we can start with the work. Yeah, good. So the work is n squared because the parallelism, like the parallel force don't affect the work. So like we're just considering the lower triangle, which is has volume theta n squared. And how about the span? N log n. Why? Yeah, good. So like if you imagine the computation DAG, some iterations will proceed earlier than others because this is like the parallel for is a binary tree, but the one at the very last one has length n because it has this inner loop which is length n, and then the depth to get there was log n. So that's why it's actually no. That shouldn't be n plus log n. I think so, because if you remember like the thing that I said before about like series and parallel, so imagine the computation DAG. The length through the computation DAG is log n to get to the span to spawn the very last iteration of the parallel 4 is log n. And each one of these nodes has like you can imagine like an attachment of length n on it. And so what is the longest path through that DAG? Would that be theta n? Yeah, so it's n plus log n, because, yeah, so you can always get this by imagining the computation DAG. And so just imagine the parallel 4, ignoring the inner part of the parallel 4 for a second. This is a binary tree of height log n. And so the way to analyze the rest of it is what is the span of each thing of each inner iteration in the parallel 4. The maximum one has length n, but all the ones of length n can occur in parallel. So again, the span is the maximum depth through this computation DAG. So this is the attachment on each node is n. The maximum depth of the parallel 4s is log n. So the total is theta n. Yeah, so the depth of this outer parallel 4 is log n. And so it will take log n span to even just spawn off the iterations of the parallel 4. But now each iteration of the parallel 4 has some stuff in it. It has this for loop and this swap inside. And the longest one has, the longest inner 4 has length theta n. And so like, imagine the computation DAG. Each one has some serial 4 iterations attached to the node. But the longest one is length n. So like it takes, in the worst case, let's say it takes log n to get to the bottom, and the last one had length n. That would be n log n plus n. That's why it's theta n. Because you fork, like you start with 1, and you fork 2, and each of those forks 2, and each of those forks 2, and so the height of that is log n. Yeah. So the work is n squared, the span is theta n, which was n plus log n, and the parallelism, you divide them, that's theta n. Questions on this part? Okay. So let's say we had 2 parallel 4s, because you can do all these swaps independently. They don't depend on each other. And so what is the work in the span now in binary forking? So like I said, yeah, go ahead. Yeah.
So work hasn't changed. We're still doing n squared swaps. But this time, but everything is independent. So we only have the span of spawning the for loops. So I guess it would be the span is log n, only because it costs that much to have.
Exactly.
And then parallelism is the ratio.
Good. Yes, exactly. So the work is n squared, the span is log n, and it's theta log n, and the parallelism is just you divide them. So the reason that it's log n is like, again, imagine the computation DAG. You kind of have like a tree, which is height log n, and each of those has another tree, which is like hanging off of it, that's height log n. The maximum path length through that entire thing is theta log n. Thanks. Okay. Yeah, this is just a way to say, theoretically, how should you write your parallel loops? So let's say we had an outer parallel 4 and an inner serial 4. One way to write this, yeah, and they're both up to n. One way to write this is that this outer one goes up by groups of 32 iterations, and this inner one just goes up by like 0 up to 32. And you're just doing some constant work inside. Theoretically, the work as compared to n, the span is log n, because the span of this outer thing is log n, and the span, and then the length of this inner thing is constant. So the total parallelism is n over log n. However, one thing that you may think is a good idea is that you go up the outer one by p, where p is the number of processors you have. And then the inner one goes up by p as well. or sorry, the outer one goes over n over p, the inner one goes over p. The total volume is still n, but the span is now n over p, because the inner loop has length n over p. And then the parallelism is now theta p, rather than theta n log n. And then this is low, because ideally you want the parallelism to be much greater. Like, parallelism is a theoretical notion. You will not achieve parallelism much greater than p, but parallelism is like the maximum possible speedup you can get. And so you want, theoretically, you want your parallelism to be much higher than p. Why is span n over p? Good, because this outer loop has p iterations, like 0, each one is going up n over p, so it has p iterations outside, and then the number of iterations of each of these inner parts is n over p. So this is a serial 4. It has length n over p, so the span of this, just this part, ignoring the outer parallel 4, the span of this is n over p, because this is serial 4. Answer the question? Yeah, okay, these are just a couple notes. So in general, you want to minimize the span and maximize, because minimizing the span maximizes the parallelism because the span is in the denominator. And from a practical perspective, ideally you would like to have at least 10 times the number of processors in your parallelism. And if you have a lot of parallelism, sometimes you can trade parallelism for, you can reduce the work overhead, or you can maybe reduce the space overhead. So if your parallelism is quite high, we'll see an example of how to do that later. Usually, yeah, so try to use divide and conquer, like spawn and sync, or parallel 4s, rather than doing like spawn a whole bunch of things one after the other. Yeah, so like this, parallel 4 on the outside, rather than like 4 on the inside and then spawn all of them, because this will serialize all the spawns, which is not useful. Another thing, yeah, so this is like a practical thing, but in practice, it costs something to spawn. Like, of course, like if you imagine implementing a parallel system that can support function spawn, like you have to move the function context and like you have to save some state, so it costs you something. And so the way to guarantee that you have practical efficiency is you want to try to maximize the amount of work relative to the number of spawns. So like you want to try to amortize the actual work that everybody is doing relative to the number of spawns that you have. Like, it's not really worth it to do a spawn for just like a single edition, for example. And yeah, so it's also, these are related. To ensure that the work is high relative to the number of spawns, you can parallelize the outer loops, because usually there's more work inside than, yeah, there's more work, like the more like volume you have. And yeah, and these are all related, so there's scheduling overhead doing the spawn, and that is the reason that we want to do more work per spawn. So this is just saying do the parallel 4 outside rather than the parallel 4 inside, if possible. Questions? Mm-hmm. Yes, so you would not want to do this because under the hood, well, this is serializing on the outside, so this would be like you spawn these off, but then the next time around you have to come here again. In general, like this is kind of simple because like this is just a parallel 4 over 2 iterations, so you could implement it as just a spawn and a sync. But under the hood, like when people implement parallel 4, often they'll do coarsening, which is like rather than spawning all the way to the bottom, they'll spawn up to some constant fraction. Like they'll cut off the spawning at like, for example, like 32 or 64 iterations. Here, obviously they cannot because there's 2 of them, but if the parallel 4 was like over this n, then it would actually probably cut off earlier than that. So this is another reason, like that this is like like work and span are theoretical notions, and they don't have anything to do with how, like for example, the parallel 4 is actually implemented under the hood. But they are a maximum found on the speedup. Because if the outer loop is serial, then it serializes the entire thing. like again, imagine the computation DAG. Like you have this one, you would have one long chain with length n, and then each of them would have like 2 hanging off of it. Whereas the computation DAG for this, you would have 2 like this in the top, and then each of those has length n. Questions? Okay, I think I don't have that much time, so we can quickly go over the problem, and then next time I'll continue. So yeah, so we're going to talk about matrix multiplication next time, and specifically we're going to do square matrix multiplication, and for simplicity, we can assume that n, which is the side length, is a power of 2, just 2 to the k for some constant k. And recall that matrix multiplication is, you can represent it as a series of dot products, where so the output is C, every Cij is a dot product of a row of A and a column of B. So the total, I think we did this like in the previous lecture, the total volume is n cubed. Yeah. And so one way, like we had this 3-loop matrix multiplication in a previous version, or in a previous lecture, and one way that we can parallelize this is by putting parallel force on both outer loops. We cannot directly easily parallelize this k because like the k is a dot product. So if we just, like all of them are writing into this Cij. So it's a bit trickier, not impossible, but trickier to parallelize over the inner dimension. And so you can't just directly put parallel 4, but this is enough parallelism. The work is n cubed, the span is n. This is like similar to the example that we had before, which is like 1 parallel 4 and then a serial for loop over n inside. This is now 2 parallel 4s, but it's just like log n plus n. So that's n. And then parallelism is work over span, that's n squared. And this is quite high parallelism for small-ish matrices, 1000 by 1000, and squared is like 10 to the 6. So we are good on parallelism on this one. And we can pick up here next time. Thank you.